It's really my pleasure, more than our pleasure, to have today Philippe Souplet, who is going to talk about a Liouville theorem in a half space and its applications to the gradient blow-up behavior for superquadratic diffusion Hamilton-Jacobi equations. Please.
Thanks a lot, Tej, for this very nice invitation. Of course, it would be even better if I could be with you in person, but as I said, it's still a little complicated to travel far away. So for this time, it will be like this. And so maybe the title, I have decided to broaden a little bit the scope of the talk. Maybe it's better to give more background. Of course, I will discuss the Liouville theorem and its applications maybe in the second part of the talk. But before that, I would like to give a brief overview of the more general blower properties for this problem, because it's better to have it in the context. So the equation is on the first slide. It looks quite simple at first sight, but in fact it has a very rich variety of behaviors and phenomena behind. So it's the Hamilton-Jacobi equation with diffusion term. So, and I'm considering the initial Dirichlet problem. And okay, now I have to move to the next slide, and maybe it seems to be stuck, but okay, now it's better. So let me give some motivation. The problem comes from stochastic control theory. So you consider a dynamical system with a white noise like this. X sub s denotes the position of the particle. Mathematically, it's a stochastic process, and the control is alpha s, and alpha s is actually, so the controller acts on the velocity of the particle. And what is the connection with the PDE? U naught, which is the initial data for the PDE, will correspond to the spatial distribution of rewards, because it's a game with cost and benefits. So at the given time horizon, let's say s equal t, the final reward is u naught at x sub t, provided x stays in the domain until time t and 0 otherwise. And now there is a cost, and the cost is power of the length of the control. The power is the conjugate exponent of p, so p over p minus 1. And this, of course, this as long as you do not leave the domain. So the net game is g sub t is, okay, u naught of xt, provided the particle has remained in the domain all the time, and minus the cost, which is, of course, the time integral of the cost functional integrated in time until the first exit time of the process. Okay, so the goal is to maximize the net gain. The value function of the game, u at x and t, is a supremum over all possible admissible control. So I do not go to details what is an admissible control, but it's part of the stochastic process theory. And then it's the expectation of the gain, net gain, conditioned by the event that the particle starts at point x. So u at xt is just that, the supremum of the expectation of the gain conditioned by the initial position. And so there is a very nice theorem due to Barl and his collaborators already some time ago, which tells you that the value function u is corresponds to the unique continuous viscosity solution of the PDE. So it's a very precise connection. So let me go back to the first slide. So the PDE is just that. And then the theorem tells you that u is the value function of the game. So the connection is can be used in either direction. Either you know something on the PDE and you deduce something on the game, or you have some intuition about the game and what is the more profitable strategy of control, and then you can say something about the PDE. in my case, it's rather the first way. So we have some PDE results which sometimes can tell you something on the game. But maybe I will not discuss too much the applications to the stochastic control problem today. Okay, so of course there are other motivations. Maybe the more convincing is what I just described. But there is also a famous KPZ model in surface growth theory, which is connected with this equation. So the gradient to the P stands for the source term, which in that case corresponds to the ballistic deposition of alumine particles on the surface. And diffusion corresponds to the relaxation of the interface, because of course an interface will start to develop when the dust fall on the board. And the surface tension of the interface seems to be modeled by this diffusion term. And in the stochastic version of the PDE, in the original KPZ model, there is also a white noise on the right hand side. And maybe your first part of the motivation just is more mathematical or theoretical. It's the one can see this equation as the simplest parabolic PDE, one of the simplest parabolic PDEs with first order nonlinearity, by which I mean nonlinearity acting on the gradient rather than on nu itself. And there may be interesting comparison with the zero order problem, the well-known nonlinearity equation, or so-called Fujita equation, where the right-hand side is just u to the power p. And maybe we will sometimes go back to this comparison. So let's start with some basic properties. So the local well-posedness. So in this talk, I will discuss the blow-up phenomena. So I assume that I have a smooth enough initial data. I don't want to discuss optimal classes of initial data, although this has been paid a lot of attention. So I start with C1 data, which are zero on the boundary. And the classical theory tells you that there is a unique maximal classical solution up to some time, capital T. And then you have basic estimates. The first very easy estimate is just the maximum principle, which tells you that the solution starting from non-negative initial data stays non-negative and can never exceed its initial maximum. So there is an a priori bound for U, so this means that since the working space is C1, this means that if the solution should cease to exist in finite time, then necessarily the subnorm of the gradient would have to blow up. So this is what is called in the literature gradient blow up, but we will abbreviate GBU. So the question is, so it's already quite different from the usual L infinity blow up. For instance, where for the Fujita equation, when there is blow up, U itself blows up. Of course, the gradient has to blow up as well, but U blows up. In gradient blow up, the gradient blows up alone. U stays bounded. So we will see this in detail. And does this happen? Then, well, this depends on the exponent. When the P is less than 2 or equal to 2, we are in the subquadratic. We are in the realm of subquadratic theory, and then there are very classical estimates in the 50s, 60s, which tell you that an L infinity bound automatically implies a C1 bound. So nothing weird can happen, and the solution will be global, and actually it will be even bounded and decays exponentially to 0. So this is not the most exciting case for our purpose. So we move to the superquadratic case, at least in bounded domain. Then it's quite known now that gradient blow-up occurs for large initial data. So there are various criteria for which provide sufficient conditions for blow-up, gradient blow-up. And one of them is just largeness of the LQ norm for some finite Q. This is not true for Q, by the way, not true for Q equal infinity. But for any finite Q, if initial Q norm is large, then you have finite time gradient blow-up. On the other hand, if you start from small initial data in C1 small, then you have global existence and decay. So we are in a typical situation where we have two, let's say, stable states, the rest state and infinity. So in between, there might be some interesting dynamics. This has been studied, but we will not, borderline dynamics between blow up and global existence, these kind of things. But it's not what I would like to discuss today, because I would like to concentrate on gradient blow up. Now there is another very, so I list a partial, I wrote a partial list of references on these basic issues. So you see it goes back to a long time ago. Now another important fact, although I will not go to details today, is the fact that after gradient blow up, any solution, gradient blow up solution, can be continued as a unique global viscosity solution. So this is again, of course, I already mentioned this because I already stated the theorem of Barl and Dalio, which tells you that, okay, the value function of the stochastic control problem coincides with the unique viscosity solution of the Hamilton-Jacobi equation. So indeed, after gradient blow up, you still have the continuation given by this global viscosity solution. And there is a very rich variety of phenomena which can occur after gradient blow up. Namely, there can be loss or no loss of boundary conditions. So this is a slightly delicate issue, because one has to go to look precisely at the definition of boundary condition in the viscosity sense. It's still zero clear boundary condition, but not in the pointwise sense, in the generalized viscosity sense, which I don't want to discuss here, but it's quite interesting. There is also ultimate regularization. This was proved by Porretta and Soissois about 10 years ago. So eventually the solution will become smooth and classical again, and will satisfy the boundary conditions in the classical sense for all large time and even decay exponentially. But in between, there might occur lots of strange things, like multiple times of gradient blow up, losses and recoveries of boundary conditions, regularization, and so on. And now there is a better, in the recent period, we have gained a better understanding of these on these things. I'll list some references at the bottom of the slide, but again, I would like today to concentrate on the gradient blow up phenomenon. Okay. By the way, since I mentioned here that gradient blow up can occur again and again at multiple finite but multiple times, this means that part of the analysis will be true at any gradient blow up time, actually. Of course, there is a first gradient blow up time, the one where the first time when the classical, the solution ceases to be classical. As I said, under some assumptions, it can become classical again, and then again cease to exist in the classical sense, and so on. So the analysis that I will describe today, to some extent, is true at any gradient blow up time. But for simplicity and to avoid too many assumptions, I will assume that we are considering the first gradient blow up time. Yes.
This is interesting. I mean, from the deterministic PD, so somehow you found out that because the stochastic process is like C1. If when you think about the Brownian motion, let's say if there is no jump, it's like C1 half log, right?
Right.
It's like you found exactly the properties that you would find on the stochastic process. Like it forms a cusp, so it's bounded, but you have the blow up.
Exactly. Yeah, you have things like that. Yeah, you have even cusps. Cusps do occur. Yeah, that's true. Cusp in the time derivative, for instance. Yeah. We will see later, singularities are exclusively located on the boundary. Inside the domain, nothing weird happens. Okay. Yes. Okay. So now let me just give a short outline of what I'm going to describe now. So I would like to discuss, as I said, the behavior of gradient blow up solutions, and more precisely, three types of questions. Singular set, so where does a gradient blow up occur? Then the time rate, and then the space profile, and maybe sometimes I will also give some information about time-space profile, because of course you have the behavior in time, the behavior in space, and the more complicated dynamics often can be observed when you want to understand the space-time, both space-time behavior, like in self-similar blow-up, for instance, or these kind of things. So I will try to split my talk into these three topics, and in the third topic, this is where the Liouville theorem will enter. Okay, so of course all these questions have been intensively studied for the Fujita equation, except that it is, as I already said, infinity blow-up and not gradient blow-up. And there is a detailed theory for the asymptotics near finite singularity, which is by now, I would say, almost complete in the subcritical regime. But in the supercritical regime, there are more and more results, very sophisticated results, but not completely, no full picture now at this point. Okay, now so let's start with the gradient blow-up set. So let me define B, set B for given initial data U0 to be the set of those points in the closure of space domain such that the gradient becomes unbounded near that point and near time t equal to capital T. Capital T, as I said, is the first blow-up time of the solution. So the main key fact is that the singular set B is always a subset of the boundary. Okay, and this is a consequence of a gradient estimate that we proved with Chizong now a long time ago, which tells you that the gradient is bounded by a negative power of the distance to the boundary, and the power is 1 over p minus 1. So this means that it's only for this problem, gradient blow-up is only boundary gradient blow-up. Okay. On compact subsets, everything is smooth and classical for all times. Okay. Still, there are variants or other instances of in this class of equations where interior gradient blow-up may occur. So I give some references here. For instance, just the simplest model is U times grad U to the P, already enough to produce interior gradient blow-up. In the case of the P Laplace diffusion, my former PhD student Amala Tushi has studied similar properties. In particular, she proved a gradient estimate analog to this one, which again implies that all the singularities are on the boundary. And some estimates of this kind, I cannot go to detail, but if let's say it depends, depending on the dependence of the constant on the solution or its possible universality, this may imply Liouville-type theorems, for instance, for ancient solutions of the problem. Ancient solutions means defined for all negative times in the whole space. But I don't want to go to details about this. But all these questions are related to gradient estimates of this kind. How do you prove such a gradient estimate? Then it's just a variant of the classical Bernstein technique, localized in space. In the elliptic case, for stationary solution, this was done by Pierre-Louis Lyons in the 80s. And these techniques can be modified to the parabolic problem. And basically, the idea is to consider an arbitrary function of this form. Eta is a cutoff, phi is some suitable nonlinear function, and grad u square. And you try to show that this satisfies a good enough parabolic inequality, and you apply maximum principle. That's the way it goes. Okay. Let me mention that estimate 1 is optimal in terms of power of the distance to the boundary, as we will see later. Okay, so this is the first fact. Now, once you know that the gradient blow-up is localized in the boundary, you could ask, okay, but what kind of subsets of the boundary can it be? And of course, a trivial observation is that you consider the symmetric case, by which I mean omega is a ball and U0 is a radially symmetric. Then it's clear that the solution will stay symmetric, and in particular, the blow-up set in that case has to be the whole boundary. Of course, this is a very elementary observation, but it tells you already that it can be the whole boundary. So what oversets? Okay, we have a first kind of results, which we proved with Yuxiang Li about more than 10 years ago, which tells you that given any boundary point, you can find initial data for which and sufficient conditions on the initial data for which the singular set will be localized in a given small neighborhood of this point. Okay, so of course it depends on how concentrated is the initial data, and also interestingly, the subnorm can be made arbitrarily small, but of course not the derivative. The idea of proof is again, it combines Bernstein type estimates with special barriers and risk scaling arguments. Okay, so maybe it's not the most exciting result because we will see a better one after. So this is next slide. In the same paper, we were able to construct what seem to be the first examples of single point gradient blow-up. Of course, it's a well-studied topic for Fujita type equations, single point or finite point blow-up. There are famous papers of Matano, Frank Merle, Freeman MacLeod, Fred Reisler. So there is a large literature on the single or finite point blow-up for this equation, but for gradient blow-up, it was not known before, apparently. So we consider, of course, we need, as in the case of Fujita equation, to have finite or single point blow-up, you need some geometric restrictions. So we here we consider the following geometric situation. We are two space dimensions, so on the plane domains, and we assume that this domain is symmetric with respect to the line x equals 0, so the vertical axis, convex in the x direction, and also this is for technical reasons, and actually this was improved later, but at that time we had to improve that. We assume that the boundary is locally flat. Here, specifically, it means that it contains a line segment near the origin, okay? And then we assume some symmetry, which I will describe later, some symmetry of the initial data, and under these assumptions, we can show that, for suitable symmetric initial data, gradient blow-up occurs in finite time, and the blow-up set is only the origin. So this means that if you look at if you draw the what should be the profile, the final profile at capital T, and in the XY plane, the surface described by the solution should have this kind of shape. So the fat line here, the fat curve, has a vertical slope at the origin. So the gradient is infinity. Actually, the normal derivative is infinite. And away from this central slice, the surface becomes less steep and is immediately, the gradient is immediately regularized when you move to the left or to the right in the x direction. This is the final shape. Okay. I will give better estimates on the final shape later. So okay, so this typically to get this, we should assume that U0 is symmetric and decreasing in x, and is sufficiently concentrated near the origin. There are some more precise assumptions, but this is the idea. Okay, this has been generalized more recently by my former PhD student, Carlos Esteve, who was able to show this kind of results in non-flat domains. Of course, symmetry seems to be a necessary restriction, but the flatness is not. It was quite technical. He made very nice, he devised very nice techniques to eliminate the flatness assumption. With Amal Atouchi, longer ago, we but in flat domain case, we were able to show similar results for P-Laplace diffusion, and then it becomes extremely technical. It's maybe a 40-page proof, but still it works. And okay, maybe this can be interpreted within the framework of the KPZ model, but I'm not so sure about the physical relevance of this. Okay, so let me give a short sketch of proof. So there are maybe 3 or 4 steps. The first step is to use an auxiliary function, which is a 2D modification of a 1D device, a famous device of Riemann-MacLeod for the Fujita equation. So is this function J here, which involves the derivative in the tangential direction plus some strange non-autonomous perturbation of u to the q with specific values of the powers. And then, okay, the idea is to use the maximum principle to show that J is satisfied first to compute a nice parabolic inequality satisfied by J, and to apply the maximum principle to deduce that J is non-positive. This is quite technical. This is the most technical step. It uses the Bernstein estimates and other devices. So once you know that J is non-positive, sorry, you integrate the corresponding differential inequality in X, and you end up with an estimate like this for X, Y small and T close to capital T, something like this. Okay. So what can you do with this? Then you have to combine it with a non-degeneracy result. So there are many experts in this audience about blow-up for non-linear equation. So if you think about the gigacone non-degeneracy estimate, the famous one of the famous achievements of gigacone in the late 80s. So this is something analogous. One can show by using barriers and again Bernstein type arguments that if you have a blow-up point, gradient blow-up point at the boundary point A capital T, it cannot be too. It has to be singular enough. It cannot be strongly dominated by this power of the distance to the boundary. Otherwise, the singularity becomes removable. Okay, so this kind of non-degeneracy result. But now, in our situation, if you look at this estimate here, the distance to the boundary is the variable y, of course, because we are talking about the bottom of the domain. And so you see that this power can be made close to 1. So in particular, it is bigger than p minus 2 or p minus 1. So in this situation, for any finite x small, you cannot have a blow-up point at x 0, because it would contradict the non-degeneracy estimate. So the conclusion is that 0 is an isolated blow-up point, and by other parts of the constructions, it has to be the only point, actually, the only blow-up point. So this is the sketch of the proof. Okay, there are some nice open problems about this because, okay, we don't know whether this it would be a reasonable conjecture that in 2 space dimensions the blow-up set would be finite. Why? Because okay, in that case the boundary is 1-dimensional. And by analogy with the famous results of, for instance, Chen and Matano or Polacek and others for the Fujita equation, the 1D Fujita equation, in 1D by typical zero number and reflection arguments, you can show, and that's what Chen and Matano did. They were able to show that only finitely many points, and Frank Merle has also results, connected results. So now in 2D for Hamilton-Jacobi, the boundary is 1D, so it's a natural conjecture. But we don't have the tools, because in 2D we no longer have zero number and the reflection principle used by Matano and others. So it's an open problem. And now if you go even to more sophisticated things, if you remember about Velázquez's famous paper on the finiteness of the house of measure for of the blow-up set for Fujita equation. Okay, we would expect the m hours of measure of the blow-up set to be finite for m equals n minus 2, but it's again an open problem because the techniques, the tools used by Velázquez and specifically the energy structure, the variational structure of the problem is not available. Okay, now let's go to the second topic. Yeah, please.
I was going to ask the question if we know the Hausdorff dimension of the singular set.
Yeah, no. As far as at this point, we only have examples of finitely many in 2D, or maybe this can be extended to axisymmetric n-dimensional domain. So then it would be it would be.
But n-2 would be an upper bound, no? For the Hausdorff dimension, at least.
Of course, an upper bound. Yeah, it can be less. Of course, it can always be single point. What I said about 2D is actually can be extended. It's not that we didn't write it because it was maybe already technical enough, but the same technique will prove the same the axisymmetric problem in NDs. So single point example of single point blower. Okay, so let's go to the second topic, which is the time rate. So there is a fundamental lower bound, which is capital T minus T to the power -1 over P minus 2. So the key number is 1 over P minus 2. So you already see a difference because for the Bernstein estimate, the space estimate was 1 over P minus 1. And so I will comment on this later. There were, okay, this final version of the result we proved with Alessio Porretta rather recently, but there were previous partial results, let's say in 1D or in radial case, or this can or less precise estimates, but of the same rate known before. Let me give the idea of the proof, but maybe very quickly because I want to spare more time for the rest. So the idea is to look for the equation for the U sub t. So it's a linear equation with a drift, and the drift depends on the gradient. And you combine with maximum principle, variation of constants formula, and you try to get differential inequality for the quantity m of t is the sup norm of the gradient in a past space-time cylinder. And by using this linear equation, or let's say, yeah, linear if you assume b to be a given coefficient. So if you use this linear equation for W plus the fact that U sub t is bounded by the maximum principle, plus some semi-group estimates, you get up with this inequality. And if you integrate it, it tells you that M is satisfies this estimate. Of course, it's not sufficient because M is the whole history of the solution, and we would like to have it only at time t. So you have to work more, and this becomes more technical. But at least the basic idea of the proof is this. Okay. Okay. Now, what about upper estimate? Sorry. Yeah. Okay. No. Sorry. First, an important remark. A consequence of this lower estimate is that the rate is never self-similar. So this is so always type 2. In other words, always type 2. So why? If you look at the natural scaling of the equation, so this means, for instance, scaling that would be satisfied by a Liouville-type backward self-similar solution, let's say in a half space, then the scaling exponent k would be p minus 2 over p minus 1. So now if you differentiate this in space, this would mean that the self-similar rate for the gradient would be given by the exponent 1 over twice p minus 1. But this number is smaller than 1 over p minus 2, so it means that the actual rate is always more singular than what would come out from the scaling analysis. So in other words, it's always type 2, which is already a big difference with the Fujita equation, for which, as well known, there exists both type 1 and type 2 solutions depending on the exponents. Here, whatever the value of p bigger than 2, it's always type 2. Okay, so now the question is this sharp, this lower bound? Yeah, please.
Sorry. Do you think that if omega is, if you take the whole space, you would have self-similar solution?
That's a very nice, very good question. But the answer is no, because in the whole space, it has been proved for a long time that there is no gradient blow up at all.
Okay, there's no at all. Okay.
But there are forward global self-similar solutions, and those are self-similar.
Okay.
Those the let's say the global self-similar solutions. They exist.
Come really from the bound.
The blow-up self-similar solutions don't exist. Yeah.
Okay.
Yeah. And of course, the whole space. So why is there no blow up in whole space? But because it's basically a boundary phenomenon, and the Bernstein estimate, which applies, tells you that the gradient has to be bounded because there is no boundary, and the gradient, the local Bernstein estimates gives you an estimate by negative part distance of the boundary. But if the boundary is at infinity, this means that the gradient is always bounded. Yes. Okay. That's one of the possible proofs. Okay. Now, is this sharp? The answer is basically it is sharp for time increasing solutions. So time, or at least solutions which are time increasing in some neighborhood of the boundary. Unfortunately, if you just take the original problem without this forcing term h of x, you have no time increasing solutions. This is easy to see because the maximum principle. But okay, still, what can show that there are solutions which are time increasing in the neighborhood of the boundary. So this is enough. But if you want to look at more tractable conditions, you can just add this artificial term, which is not completely artificial because in the KBZ model, for instance, have such kind of term. Here is deterministic, but it's like in the KBZ. And the sufficient condition for time increasing will just be that U0 is a subsolution of the elliptic problem. So under this assumption, plus some technical restrictions, which at this moment we don't know whether or not they are necessary. The conclusion is that this is sharp. There is a two-sided estimate with the rate 1/(-2). Okay, so this was proved in one space dimension first by Guan-Hu and with some improvement in paper with Porretta. This was extended in the radial symmetric case. And now if you look at more general geometries, it's becoming more delicate. And at this point, all the results for of this kind for time increasing solutions require P at most free. So this is in our recent paper with Amalatushi. So sufficient conditions are omega convex, P less than 3, or maybe including 3 if it's a ball or an annulus, of course without symmetry restriction, otherwise it's covered by the previous result. And now if you take any domain, not necessarily convex, and P is at most 3, then it's still true, the upper estimate is still true up to an epsilon. Okay, so probably it's technical, but the real restriction seems to be P equals 3. And P equals 3 actually already enters in some famous papers on that subject. The paper by a series of papers by Pierre-Louis Lyons and Jean-Michel Lasserie on the stochastic control problem for some of the estimates which are crucial in the stochastic control theory. They also require P at most 3 for some reasons, and it's not clear whether it's technical or not. So at this point, we are stuck with P equals 3 for some of the results, and more will follow. Okay, that's a good open question too. Now, this is of course only for time increasing solutions, and like in the case of the Fujita equation, where time increasing assumption introduces a lot of rigidity in the problem. Here it is the same, and if you relax this assumption, then you have all kinds of possible more singular rates. Okay, I skipped the proof because I don't have time. So let me go to the recent results that we obtained in collaboration with Noriko Mizoguchi, where we've obtained a complete classification of the blow-up rates in 1D. So the question is just this, either a bounded interval of a half line, assuming that, let's say, 0 is about a blow-up point, then we were able to show that there must exist an integer, positive integer, such that the rate, so the rate will be just the derivative at the origin in that case. It's not difficult to show. And then the rate is L over P minus 2 for some L and for some constant C, which is the constant is really a limit. It's not just a two-sided bound, it is a limit. And conversely, for any given integer, positive integer, there exists initial data and a constant such that the solution has this rate. So it's a complete classification. And so we can say more. We can also classify the space-time behavior in that case in 1D. So it's a kind of bubbling result. So define the okay, in 1D it's very easy to compute the steady states. It's just the ODE, and they constitute an ordered family of curves, and they are explicitly computable. And so let's say there is a bubble. The bubble is just the most singular, the only singular one, which is on top of the others. It's just a power of x to the power p minus 2 or p minus 1. We already saw this exponent come up in previous slides. So this is the only singular solution. All the others are give a foliation connecting 0 and v. And okay, and so and actually the others, the regular ones, are given by translates of the singular ones, singular one. Okay, so this is the bubble, like in the Leibniz equation, let's say Sobolev critical. Okay, so what we show is that in a small boundary layer, the behavior is already described by quasi-stationary version of the steady state, but by mean okay, sorry, capital U is capital V actually. It's capital it's U, no, it's U. Sorry, capital U A of t. So it's this U of A, except that the A depends on t, and as t goes to the blow-up time, A of t behaves like U sub x to the power 1 of minus p. So more precisely, if you have a rate like this, then you just plug it here, and you have the rate. You have the size of the boundary layer in terms of capital T minus t. Okay, plus some remainder term. Okay, so this is the bubbling behavior in a small boundary layer of this size. And how do you characterize L? So it is L is actually the number of vanishing intersections of the solution with okay, this capital U is just capital V, so the singular solution. So the number of vanishing intersections of the solution with the singular steady state as t goes to capital T. So what is vanishing intersections? Okay, you have zero number theory, which tells you that the number of intersection is a non-increasing function of time. Okay, this is the Sturmian theory of Andrenent, Matano, and Galaktionov and others. So it applies here, and it tells you that the number of intersections is decreasing or non-increasing. So it has to be constant in some time neighborhood of the borrowed time because it's discrete. So call this, so which means that for t close enough to capital T, this number of intersection is constant. Okay. So, and now you can, so and they are also non-degenerate, so you can track the zeros because the zeros are non-degenerate, they are smooth function of time. So you can track them, trace them, and some of them will stay bounded away from zero, and some others will collapse to zero at the final time. Okay, you can show that oscillation is not possible. Either they stay bounded away from the boundary, or they collapse to the boundary. Okay, and so the vanishing intersections are those which collapse to the boundary. So there is an integer number of them, call it L, and this L is exactly the L that enters into the rate here. Okay, so it's a very precise connection between the geometry of the graph of the solution and its blow-up rate.
Philippe, just a small question. When you take an initial data, how is the flow going to select an integer rather than another one?
Yeah, that's a very nice question. I don't have a precise answer to this. We have topological arguments to select, to construct special solutions with a given L, but give me a solution, I'm not able to see how it will select.
You don't think that
depends on too many things. It's difficult to answer this kind of question.
Because here the approach is based on maximum principle or on
zero number theory.
Yeah.
Actually, on Braid group theory, I will go back to this next slide.
Okay. But if you look at the linearized operator around these of t,
sure.
probably it corresponds to
eigenvalues. Yeah, of course, eigenvalues and eigenfunction. Of course, you can linearize, and this is part of the proof. in the Herrero-Velasquez or Merle-Raphael style, but this is okay only for special solutions. But our theorem classifies any solution. You see, so when you linearize, usually it's a way to construct special solutions, or maybe to decide what the solution will do in the small neighborhood of the bubble.
Okay.
But here we are able to classify all possible solutions. So it's a different kind of result.
Yeah, this, I mean,
so it's difficult to see it on the linearization. Linearization is used also in our proof. I will explain.
But this is the strongness of the maximum principle. I think it gives way more stronger.
Yeah, but maybe the next slide will give some partial answers to your question. Okay. There is one more point that is also contained in the complements this theorem, is the stability issue. So now, of course, you know, and of course, your group and Nadia's group has a fantastic result on stability of blow up these things or restricted stability. We only have the following small result. We can characterize when the gradient blow up time and the gradient blow up rate is or is not stable. So the time is stable, or let's say continuous. It means continuous with respect to initial data, if and only if L is odd. First thing. Second thing, once it is odd, of course, if T itself is not stable, then it has no meaning to ask about the stability of the profile. But if T is continuous, so assuming L is odd, then the rate and the profile are stable, if and only if L equals to 1. So only the first mode is stable. Of course, it's a natural guess, also considering recent results on other problems that you and your group studied, but there might be some codimensional stability hidden behind, depending on L, but we don't have, apparently the structure of the problem is not completely, it's not clear if we can do this, but maybe, but looking more closely at the linearized operator, maybe in some neighborhood of a bubble, we could say something, but we have not yet studied this. Okay. I was sure you are going to ask the question, so I answer in advance. Sorry. Let me give a short sketch of proof. Unfortunately, if I want to have some minutes for the Liouville theorem, I should speed up a little bit. Thank you. Okay, so in the theorem there are two parts. So part A is the classification. Part B is the existence of for each rate. So let's start with part B. Actually, that's the way the proof goes. So part B is construction of special solutions with precise space-time behavior. It's basically it's a modification of the Herrero-Velasquez technique for type 2 solutions. Of course, there's also the Merle-Raphael technique, and they both have advantages and drawbacks. And for this problem, it was maybe easier to use the Herrero-Velasquez technique, more convenient. So the idea is to first go to same variables like in Giga and Cone, then use match asymptotics to identify an inner regime and an outer regime. The first one would have quasi-stationary behavior, like bubbling, and the other one would correspond to the linearization around singular steady state. And then you can compute the spectrum and the eigenvalues. Then you match formally, and then to make the matching from formal to rigorous, you use a priori estimates and topological degree. Okay, so this is the map, the root map of Herrero-Velasquez and Merle-Raphael and others. So this is, I mean, we are not innovating in this respect, but still the proof is 30 or 40 pages long as usual, because, and of course, all the computations are different because the problem is also gradient dependent, and so you have to work more, although the technology is by now something classical in some sense, but always difficult. Okay, once you have proved part B, so you have, for each L, you have a special solution with the sharp rate. Now the idea is to use Braid group theory and a zero number. Actually, Braid group theory is a kind of sophisticated version of zero number theory. And in zero number, you compare two solutions. Here with Braid group, you can compare three solutions. So it's much more powerful. And the three solutions that will be compared are, of course, the given solution U that we want to analyze with L, let's say L with L vanishing intersections with the steady state. This is the assumption. Capital U is a singular steady state, and V will be the special solution that we just constructed, which has the same number of vanishing intersections as our solution U. So they share this. They have in common that they keep for all times prior to capital T the same number of intersections with the singular steady state. So this makes things quite rigid. And of course, we can always by shift assume that they blow up at the same time. Okay, and now what we do, okay, now I have to be very quick because it's a complicated theory. So now we consider the braid of 3 strands associated with the 3 curves. So let me remind you that the way to do this is to lift the curve from 2D to 3D by introducing the derivative direction. So the third axis will be v sub x, which means that if, consider this first crossing, if the fat curve have a larger derivative, which is the case here at the crossing, assuming, of course, all intersections are not degenerate, which can be adapted in practice. So in that case, you draw the curve in front of the fat curve in front of the other one, because it has Vx larger than the other one. So this is a way you lift to 3-dimensional space. And once you do this, you consider the braids, the formal braids associated with these pictures. So you see, it's just the way it goes by passing above or underneath, okay, like a braid of 3 threads, 3 strands, okay. And then you use the Artin's representation, which means that you have two generators, X and Y, corresponding to third passing over second or second passing over first, okay? And it's known in the basic braid group theory, but any braid can be a positive braid with orientation, can be generated, finitely generated by these 2 generators, okay? And once you do this, you use the Matano's parabolic reduction principle, which is a kind of entropy principle. The entropy principle is like the 0 number. In 0 number, the entropy principle is that the 0 number cannot increase in time, okay? In braid group theories, the entropy principle is that the number of crossings cannot increase in time. And so it means that up to topological equivalence, this is a delicate but important point, you can only lose x squared of y squared. That's the only thing that can happen. Okay, which means that some crossings disappear. And if you combine this plus some computation of very specific braids, plus the fact that U and V keep the same number of intersections with the third one, with capital U for all times, then you can show that the intertwining between U and V has to remain the same up to final time, and this, by comparison, gives you the rate. Okay, so it's a very schematic proof, but it's difficult to say more. Now, let me move to now the final topic, space profile. So space profile, first Liouville. So the Liouville theorem, which I promised in my title, it appears at last. You consider the related elliptic problem in the half space. So why half space? Because we know that its boundary, all dynamics is on the boundary. So it's natural to after zoom, after straightening, it's natural to look at the corresponding half space problem. So the theorem that we proved with in a recent joint paper with Roberta Filippucci and Patricia Pucci is that for p bigger than 2, any classical solution of this, not assuming any bound, has to depend only on the variable xn. So the normal variable. So it has to be one-dimensional. So it's a symmetry result in the kind of like in the de Giorgi conjecture or these kind of things. Okay, first the whole space case was proved by Pierre-Louis Lyons in his classical paper, and then it says that in the whole space, the only solution are the constants. Okay, so this is the theorem. It's quite simple to state. The proof is not too complicated either. Let me skip this. The proof, let me sketch the proof. You consider you consider tangential translations, let's say fix any vector h in the tangential plane, and you consider, of course, the difference between v and its translate. Okay, and you want to show that it is zero. If you show it is zero for any h, then it means that the solution is one-dimensional. So assume for contradiction that, for instance, the supremum is positive. Then you go back to the local Bernstein estimates of Lyons, and since the distance to the boundary is y, here it means that grad v is bounded by y to the negative 1 or p minus 1, and you can integrate, because this is integrable because p is bigger than 2, so this power is less than 1. This is very important, and this is a big difference between the subquadratic and the superquadratic cases. Then you can integrate up to the boundary, and so v itself has to be bounded by y to the positive power p minus 2 or p minus 1. In particular, it is bounded at finite distance from the boundary, and this already tells you that the supremum is finite, because this is just difference of two bounded things, so it's bounded, so supremum is finite. And the supremum, if it's positive, it has to be localized in a finite strip, because in far away from the boundary, the first part of the Bernstein estimate will tell you that z is very small for h fixed. So the supremum, if it's positive, has to be taken in a finite strip. Then you do translations parallel to the boundary, and you use some compactness procedure, again based on Bernstein. And this shows that after translating and compactification, this means that the supremum has to be localized actually at a finite point. But so z is actually z infinity. This is the limit after passing to the limit. It's very easy to compute the equation. It's the linear equation with a locally bounded drift, and it's zero on the boundary, but this contradicts the strong maximum principle. That's it. So, okay, basically, okay, I skipped some details, but this is basically the idea. It's not very difficult, but it has plenty of applications. So let me mention the application to the space profile. So first application, gradient U is bounded not just by the Bernstein estimate, but Bernstein with sharp constant, d over p up to some epsilon, and d over p is just a constant of the ODE. So it, of course, cannot be improved because for the ODE, it's explicitly like this. So up to some epsilon and some reminder, the gradient is bounded by this sharp estimate. And moreover, it is sharp at any gradient blower point. So it improves the non-degeneracy result à la Gégacon that I mentioned before. In fact, as a consequence of the Liouville theorem, for any gradient blower point on the boundary, you can show that the limiting profile of the gradient in the normal direction is this. Nu is the normal, inner normal. So in particular, the final profile at capital T satisfies exactly this, the sharp constant times the negative power of the distance's boundary, and this is in the normal direction. X minus a is orthogonal to the boundary. Okay, of course, there were early results like this in 1D quite long time ago. This was almost 30, more than 30 years ago, but well-known paper by Likakos, Bates, and Grant. But now this is quite complete general in any space dimension. Maybe it's also a natural question: can one remove this epsilon? And the answer is yes. Of course, there is some price to pay. The price is you have some remainder term, but of course it is better than this epsilon here. And this has some further applications which I don't have time to discuss for the rate. And but up to now, so we did this with Amal Atushi in the same paper that I already mentioned, but it requires some restrictions. For instance, p less than 3. Strangely enough, if you want to go this far in the sharpness, you have to restrict, and some geometric restrictions. This we can prove for omega convex, or we can, of course, in a ball or annulus, we can do it without any restrictions, either on p. But it's open whether such an estimate can be true in a general situation. Now, more consequences of the Liouville theorem. Of course, once you know the behavior in the normal direction, it's quite natural to ask what is the tangential behavior, because of course you have a single point, maybe a single point gradient blow up, and so in the normal direction, we know how it goes, and the tangential direction, we would like to know how fast it's becoming smooth, the final profile. Okay, the consequence of Liouville theorem is that it has to be more singular than in the normal direction. The same power, but here x moves not perpendicular but parallel to the boundary, and then the limit is infinity instead of infinite. Okay, so that's one thing. And another maybe more even more interesting application is that you have asymptotic simplification of the equation in the singular regime. So in the zone, in the part of the space-time domain where the gradient is very large, this can be made precise. Actually, the two relevant terms in the equation, I write the equation in 2D like this. So the box terms here are the normal component of the diffusion and the normal component of the gradient, and these are equated asymptotically, which means that the tangential derivatives and the tangential part of the diffusion is of smaller order in the singular part of the solution. So this is a real analog of the famous Merle-Zag result for the Fujita equation. For the Fujita equation, let me remind you that Merle-Zag in their famous 98 paper proved that the asymptotic simplification in the singular regime is the ODE behavior. So the solution behaves like the ODE. This means that the diffusion becomes asymptotically of smaller order. This is for subcritical power in the large part of the solution. And this was proved by means of a new, at that time, new Liouville-type theorem for ancient solutions of the problem. And here we prove it by means of also Liouville theorem. Our proof is a kind of adaptation of the Merle-Zag proof to our context, the proof of the asymptotics. And but the big difference is that the time direction is now replaced by the normal spatial direction. So, but other than this, it's this kind of ODE simplification, simplifying mechanism that can be observed asymptotically in the singular part of the solution. Okay, there are more predictions which I skip. And now let me conclude if I have a couple of minutes. Do I?
Yes, please.
Thanks. I would like to say more on the tangential profile, because the tangential profile, which is, of course, obviously a very interesting subject, because the dynamics along the boundary can be expected to be much more complicated than the dynamics in the normal direction. Because the normal direction, it is universal due to the Bernstein estimate, but in the tangential direction, one can expect many possibilities. So up to now, the only result is this one, which says that the tangential profile is slightly more singular, at least slightly more singular than the normal profile. And in fact, this is a general result. So maybe it's okay. It's here. I reproduce the same statement here. So this is the general result which I just already mentioned. The question is, along the boundary, how fast is the gradient damped away from the gradient blow-up point? For instance, in case of single point gradient blow-up, or if you blow up on the curve on the submanifold of the boundary, if you move away from this manifold, how fast is the gradient becoming regular again? Okay, and then this is just a basic result. It doesn't tell you how more singular it is. This is the infinity, but we don't know how fast. And so there are partial results. No, they are complete results, but under special assumptions. So this what we had proved actually before in another paper with Alessio Porretta. We were able to construct sharp space profiles in 2D. So we go back to the situation of the single point gradient blow-up theorem that I mentioned before. So I'm a locally flat domain. Let me maybe show this slide again. Okay, yeah. So this is kind of domain which I'm considering, and it has a flat part to simplify maybe for technical reasons with this kind of symmetry. So this, we knew that we have solutions which have single point blow up at the origin. Now we consider the solution, and what we would like to do is to compute the profile in the tangential direction in this surface of this shape. Okay, so let me go back to the new slide. So under these assumptions, or again assuming p not larger than 3, the same kind of restrictions appear again. So we have computed this profile. So this is the final time in the XY direction. So in the Y direction is all, of course, like before, if you just freeze X or take, let's say, take X equals 0, you have the central slice, which corresponds to the fat curve here. And so it's just again, sharp constants time Y to the 1 over P minus 1. So just again, the Bernstein estimate. And then if you move to the right or to the left, the tangential contribution appears. So this is this power of X. So it's a little complicated, the power here. But if you now take, let's say, Y equals 0, so you want to compute the normal derivative on the boundary at given X, okay, then the profile is X to the power minus 2 over P minus 2. So the new key number which appears here is 2 over P minus 2. And we expect that this should be the most stable profile among a big family of possible profiles, whereas the indices might be, let's say, even powers of 1 over P minus 2 or something like that, maybe more rates with other integers bigger than 2, but it's just conjectural. We have absolutely no proof of this. This proof is already quite complicated because the problem has no variation structure, and so it makes things more delicate. Basically, we have to use things like formal linearization or some kind of asymptotics, plus a lot of maximum principal bounds. Okay, actually, the lower estimate is true for any P, but the upper estimate is open for P bigger than 3 in this theorem. So we can observe that we have 3 different rates. In the normal direction, it's 1 over minus 1. It's self-similar. In the tangential direction, it's 2 over minus 1. So this is a number which appears here. Okay. And in the time direction, for, let's say, for monotone in time solutions, it's 1 over minus 2, which I already mentioned. And so the last two are non-self-similar, and the first one is self-similar. So it's a strange mixture of partial self-similar and non-self-similar behaviors, depending on the direction. Okay, now if you compare with the Fujita equation, the stable profile is completely isotropic. So it's a quite different situation. Let me give you the heuristics and maybe a brief sketch of proof of this last theorem for the sharp profile. Let me comment on the possible heuristics for these magic numbers, 1 over P minus 2, 2 over P minus 2. So they are basically a consequence of the maximum principal bounds that you get for U sub t, for U sub x, and partially one-sided for U sub xx. This you can show by maximum principle. Now you look at asymptotic balance near singularity. So you go back to the balance in 2D. And of course, only the black terms become dominant in the singular regime. The others can be ignored, at least formally ignored, thanks to these bounds. Okay, ignore just, of course, in the first rate, because in the next order you have to worry about what these terms look like. Otherwise, you don't see anything, of course. So this is the usual thing. So this suggests that there is a quasi-stationary approximation, at least formally, again with this foliation, this family of steady states which describe the bubble. And but the question is how to parameterize it, how to parameterize these curves in the tangential direction by these curves moving along the manifold of steady states. This is typical quasi-stationary approximation. So the idea is to do modulation, a modulation device. So the modulation would be at y fixed with parameter a function of x and t. So it's modulation in the slow variables, let me say, so time and tangent. And if you compute, the formal equation for this modulation, you can see that these numbers are the minimal exponents which are compatible with the maximum principal bounds. So you can compute many possible a as a modulation function, but if you want the approximation to be self-consistent and also compatible with the maximum principal bounds, then the numbers have to be at least 1 over P minus 2 and 2 over P minus 2. And it turns out that you can rigorously construct solutions for which these numbers are realized. But be careful, you can also find approximate solutions where the exponent can be much larger, actually. So in that case, it's not enough for proof. It just suggests that there might be also more singular profiles. Now, the rigorous proof, again, is based on this maximum principal bounds plus this also shear derivative bound. And then the lower profile, you have to combine various things. You can do direct OD analysis on the central slice. You can do rescale Harnack type inequalities at the final time, elliptic type, moving on a special parabola, which is suggested by the asymptotics. And then you can do some averaging and you end up with the lower estimate. It's quite technical. And the upper is even more technical because then you have to try this modulation equation, but not at the level of the PDE, but at the level of the auxiliary function. So it's like the auxiliary function, which I mentioned before for single point blow up, but you need one more term, it's slightly more complicated. So you compute the parabolic inequality for this. For suitable exponents, you have a parabolic inequality. So you apply maximum principle, it gives you that this is negative. And then it's not enough to have the upper estimate, because then you have to combine it with these local regularizing barriers, which are inspired by the modulation equation. And if you combine everything, you get up with the upper estimate of the profile. So that's all for the proof. And maybe open problems are, of course, over tangential profiles. And ultimately, could we hope for a classification? But at this point, we have no idea how we could do this. So I will stop here. Thank you.
Okay, thank you. Very nice talk. Are there questions in the audience? Okay. So maybe I have two questions. So
yeah, sure.
This P equals 3. Do you think that this upper bound is missing because actually the speed is probably not that one? It's maybe faster, no?
Well, it's difficult to say because now there are many papers now where this P equals 3 enters as a technical limitation. Heuristically, there is some interpretation of this P equals 3 at the technical level. The technical level, if you look at the linearized operator, there are some natural quantities which are sub or super solutions of the nonlinear of the linearized operator, if and only if P is less than 3.
Okay.
Okay, that's not a proof, of course, that something different might happen, but at the technical level, something seems to change for the linearized operator at P equals 3, but it does not appear when you linearize to compute the time rate. For the time rates, you have no limitations on P. It's the theorem with Mizoguchi is okay for any P bigger than 2. So it's not. It depends what you want to do with the linearized operator. If you compute the spectrum and the eigenfunctions, then there is nothing to do with P equals 3. It works perfectly fine. But if you want to combine the linearized operator with the maximum principle, and this is what we do in some of the other results, this is usually where P equals 3 enters. And in the paper of Lasserie and Lyons, on stochastic control, they have these kind of limitations also, and the reasons seems to be similar. So I have no idea if some different
but
phenomena
are they numerics where they probably predict what's happening at P equals 3?
That's a good point. I should look at this. I don't have it. I don't have in mind what the numerics say, but it might be.
Because now, I mean, when you rescale, you have like the scaling terms, which when it's type 2, like here it's non-self-similar.
Yes.
Asymptotically, the scaling terms disappear, right?
Right.
And maybe if one would include those terms in the linearized operator, maybe one can see the relation between P and the time also. But then the eigenvectors becomes time dependent. I mean, the linear operator becomes time dependent.
I see.
And maybe one can see that when P increases, it increases the number of positive eigenvalues, or I don't know. But,
this would be a good way. Of course, since we used the Herrero Velasquez, which was easier in our case, we use the LAGA strategy, then in their framework, the eigenfunctions are time independent. But in the Mel-Raphael framework, of course, something different.
There is a new approach where what we do in the inner region, we construct eigenvectors, and we do also in the outer region, and then we match them. And then you can get, because the scaling terms, if you are on a compact set, are negligible. So then you can construct things so like eigenfunctions that are a perturbation of the stationary solution. And far away, so those terms becomes the scaling term becomes important. Donc now you take them into account, but you neglect use the fact that the soliton or the stationary solution is decaying, so then it becomes negligible, and then you can solve somehow the ODE, and then you have another solution, or I mean eigenfunctions in the outer region as similarly at what you did, but then you glue them and you get time dependent eigenvectors and eigenvalues also. And
but
then
please.
And then they depend on capital. So the eigenvalues depend on time and on P also.
Okay.
So I think it gives also I think it gives a better intuition why you would have those exponent L in the speed. Like it tells you that if you start initially, if you excite such eigenmodes, let's say eigenmodes, then it will give you such speed initially.
I see.
But I mean, what is interesting here is the relation to the boundary of the domain. This is what I
exactly
like.
because of course the result with Mizoguchi with matching inner outer region and so on was in one space dimension. So it was time evolution, of course, but it's a completely different story, because now in the last slide we have to deal with two space dimension and with the tangential direction, and we already know that in any case the blow-up profile is completely anisotropic. So I wonder, do you think your techniques would be suitable to construct at least special solutions with higher modes of tangential profile?
Maybe, I think, because I think the idea comes from the paper of Mel, Raphael, and Colo, where they construct an anisotropic solution for the heat equation.
That's true. Yeah, that's right. Yeah,
probably it could.
Okay, then you're right. I remember this anisotropic paper, so maybe one should try to get some ideas of that. Yes,
maybe it's possible, but I think in the paper they removed the proof about the eigenvalues. It was like 60-page long. They just remove it. This is what I heard. So that the paper is smaller and it can be accepted in a good journal.
So we have to publish the eigenvalue computations somewhere else.
Somewhere else.
Otherwise, people are lost. They don't know how to compute the eigenfunction.
Yeah, that's problematic.
But okay, but that would be nice to look at this problem, because I must say I didn't have the energy up to now to do the full linearization story of the tangential components in the general. You know, in this, because here we have these monotonicity assumptions. Okay, not written, but essentially we assume that the solution is symmetric in X and decreasing in X direction. And then you have a lot of information coming from the maximum principle thanks to this. Really a lot, and very substantial information, already very technical. But if you don't assume any symmetry or any monotonicity, then of course you have to play with, presumably with higher modes of some linearized operator, which I never tried to do the full computation of these tangential modes, you see.
But I think, exactly. So one would have to pay the price. I mean, like, maybe it would be a weaker result, but at least you could maybe construct an example for P equals 3 or.
Oh yeah, of course, yeah. P equals 3 has from the algebraic point of view, there are some things which are easier to compute, but you lose some insight also. restrict yourself to a specific
No, I think,
power,
yeah,
you
one
lose
should
some.
be in general. But
Yeah,
I guess, okay, I think if I come to Paris, we can discuss.
Why
or,
not?
Or if
Yeah.
you
Yeah.
if you want to visit us in the fall.
No, it would be a very good problem. Yeah. Okay. Mm-hmm.
So thank you. Okay, are there other questions just in case in the audience? Okay. So thank you again.
Thank you, all of you.
And I hope to see you soon.
Yeah, me too. Thanks again for the invitation. It was nice. Bye-bye. See you.
Take care. See you. Bye.